All right, we are going to start off today going into what caused us confusion last week, which was monotones. Monotonicity. All right. Something is monotone if it is always increasing, and I want to clarify one piece in here. And I'm just going to simplify it this way. For all A and B elements of, let's call it, of real numbers, if, let's do it this way. If A is greater than B, that implies that f of A is greater than or equal to f of B. So if we have 2 points, call them A and B, A bigger than B, then the function's value at A is bigger than or equal to the function's value at B. So that means it's growing. Now, I want to clear up that inequality sign, because the last time I didn't put the bar under it, and that led me to think to myself, well, wait a minute, if a function hits a stationary point or a horizontal tangent, if it did this, if it went to a horizontal tangent right there, well, not really. If it hit a horizontal tangent, would it still be monotone? Okay. Does it always have to be increasing, or can it lay flat for a second, or a little while? And in fact, that's the difference of the bar. The bar underneath it says that yes, it can still be monotone if it's lying flat for a second. Okay? So this is math speak. And I say that because math is a meta language, in that I could walk up to a Russian paper, not knowing Russian, and look at the math and know what the math was doing. What were they talking about? Because the symbols are kind of universal, and they all describe basically the same kind of idea. All right. I should be clear, this is monotone increasing. And of course, monotone decreasing because we all have smart boards handy. So yeah, A is farther along than yeah. So anyway, let's clear that up. Now, the whole point of all of this is to find the extrema on a closed interval. Okay. Now, let's talk about what I just said, because I just talked about a couple of words in there, and I want to make sure that we understand what we're talking about. Open and closed. Okay. A closed interval would be something that contains its endpoints.
And we can usually write that in two ways, but one is, I would say, a little bit more sophisticated than the other. That is a closed interval because I have the bar underneath it. Okay? It contains both 1 and 5. This is equivalent to saying okay, whereas the bracket notation indicates whether it's open or closed. This is not, well, let me just move that over and I'll do it again. And this is where confusion creeps in because people look at that and they say, hey, that's a coordinate pair. No, it's an interval. Okay? They want to say, you know, x is 1 and y is 5, and because they look alike. You know, we're kind of abusing the notation a little bit. But there's only so many brackets that we can use. We have brackets, braces, parentheses, and a couple others, but that's about it. All right, so this is closed, and this is open. Okay. And one of the takeaway messages from this, and this is where a lot of people kind of drop the ball, is they forget to check the endpoints on an interval. Okay. And that was one thing that I wanted to not only. All right. So let's get a vocabulary term. A critical number or a critical value. Is where is a point, an x value, that produces produces a horizontal tangent. So it's a x value that produces a horizontal tangent, or it produces a point where the function is not differentiable. Okay, let me show you that graphic. So something like we're really bad for that. All right. Okay. So these two places I have horizontal tangents. Those are both critical values. Whatever x value that is, those are critical values. This is also going to be, and follow this up. This is also going to be a critical value. Okay. We discussed this once for a minute or two. I can't take a derivative when I have a point that is sharp like that, you know, a cusp like that. Yeah. Now, if we think about that for just a second, you know, my derivative could be that. And if I'm good about it, I might be able to take this off. See if I can do this. Sometimes it works, sometimes not. Very close. All right. So if I think about a tangent line on that point, this thing could teeter, and I really wouldn't know just exactly what is the slope at that point, you know? Because if you think about it, if you're at the peak, if you're climbing up a mountain, you know, you're pointing in a certain direction. right? You're pointing up. You're either climbing on a really steep slope or you're climbing up a slow slope. But when you get to the peak of the mountain, at that top of the rock, are you pointing up? Are you pointing down? Are you pointing horizontally? You know, you're just standing at the top of the mountain. There's no direction for you to go in, right? You can go in any direction. You see, so at a cusp, that's what we call that. At a cusp, we can't take a derivative, okay? Other places where we can't take a derivative are where there's a hole or a gap, okay? So if we have something that goes like this, at those points, here, right there, I jump. So what is the derivative there? You know, I could be, an even more pronounced example would be like this. You know, I can climb, as I go from the left to the right, as I creep up here, I'm climbing. I have a positive slope. But as soon as I fall down to that next point right here, I have a negative slope. So which am I? Am I a positive slope or am I a negative slope? You know, and even if the slope is the same, where is it? Who's to say? Okay, so wherever it breaks, whenever we have a discontinuity, okay, I can't take a derivative. Or whenever we have a point that has that sharp cusp, that's a critical point. And those are the places that you want to test. Okay? Because when we're looking to find extrema, all right, extrema occur wherever you have a horizontal tangent. But remember, like we said, we could have something that goes like this. If you just put all right, so I could have, all right, so I have a lousy draw. Alright, so here's an extrema, all right, but I could have something like this. Now, for a moment here, we can see that that is definitely got a horizontal tangent, right? But since I can't take a derivative at that point, right, I don't know if that is a minimum or a maximum, right? So since I don't know if it's a minimum or a maximum, I have to check it, right? So any place that you can't tell, you have to stop and look at it, all right? So we have this text that allows us to find horizontal tangents. But whenever you have a place that you just don't know, because you can't take that derivative, you have to manually, look at it and give it a piece of examination. So here are the places to check. All right. One. Okay. And these two have a name, and these are called critical points. miss too much that you're not going to get today. Yeah. Yeah. Now, I will warn you. The first one is what you're probably going to do when you're starting a problem. You're going to be like, take a derivative, set it equal to 0, find the places where the horizontal tangent exists. Wonderful. And then it's the second and third that people forget to do. Okay? All right. Let's try. It's kind of straightforward. Now, by the way, just because you have a first derivative equal to 0, that does not mean that that point is an extrema. Okay, this might be misleading. It's almost kind of appropriate that it's falling. All right.
And here's an example of why that would be misleading.
Take the function y equals x cubed. At the point 0, 0. Okay. I look at that. Right? We set that equal to 0. So that is definitely a horizontal tangent, but it is neither a maximum nor a minimum. Okay. And one way that we can check and see if it isn't, we can convince ourselves, even if we didn't have a graph, that isn't a critical point. I'm sorry, that isn't a maximum or a minimum. It's by taking the second derivative. When we take the second derivative, that tells us if it's concave up or concave down. Okay? And if we look at that graph, we can see that it is neither concave up nor concave down at that moment. Right? So when we take the second derivative and set that guy equal to 0, x equaling 0 says, hey, I'm not carving up, I'm not carving down, I'm chilling at a horizontal tangent. Right. Yeah. Okay. So let's actually do. You guys want to do work on this one? Can you go back? Oh, sorry.
So when we see that x equals 0, then we should take a second derivative.
Yes, it is a safe thing to do. To tell you what you see, because all you know is that there is an extrema. You don't know what kind of extrema. Is it a minimum? Is it a maximum? Or is it lines? Okay. But the second derivative tells you concave up, concave down, or neither. Question. Okay. I have an example. You know what? Let's do it. Can I borrow that? I can go top. All right. Please kill anything that's up there. It's all old. Okay. So this is the one that we ended with last time. And let's pick an interval -10 to +10. Right. If you need another eraser.
Does anybody need an eraser?
I think I need one.
Sure. Can I go? So you're going to set that guy equal to 0 to find your stationary points, your critical points, critical values.
Lots of different terms depending upon which book you're using, that kind of thing.
Okay, so everybody put derivative. Simplify. Seven equals to 0. All right, and factor the living daylights out. All right, so those are the two places that produce a horizontal tangent. I don't know right now, without looking at a graph or without doing any further work, I don't know if those are maximal or if those are minimal. Okay. The second derivative will tell me if it's concave up, concave down, or neither. So we're going to take the second derivative and we're going to plug in those values to see what it's doing at those places. Okay. Now, you can, if you want, take a derivative of him, right? But you can just as easily take a derivative with the GCD removed, so you can send it to 0 anyways. But I'll be fair. No, not set it forward. This one you're not going to say 0, so I'm not interested in finding out where it changes. I'm going to talk about that later. All right, so this is my second derivative. I just wrote it twice for no reason. Okay. So we're going to take the second derivative and we're going to plug in this or this and this whole. Okay. So f double prime of 3. All right. Now, realistically, I don't really care what the value is. That doesn't really interest me right now. All I'm really interested in is whether it's positive or it's negative or it's 0. Okay? Because remember, what does positive second derivative say? Concave up, right. So does that mean I'm a minima or maxima or what? That means that I'm a minimum. Now, I don't know if it's a global or a relative. All I know is that it's curving down, and this point is sitting at the bottom of that curve. And this is curving up. Sorry, this is curving down, right? I have a negative concavity. So this is a maximum. But what kind of maximum? I don't know. No. Right. So this could be relative, global, no idea yet. Okay. In order to find out if it is global or it is relative, what we have to kind of do is have a picture of this interval in our mind, or at least what's going on in this interval. So remember, this is where a lot of people tend to stop prematurely, and what you really should be doing is looking and saying, what other points could it be? Check your endpoints.
you plug it into?
No, actually, hold on. So, for example, because I know a little bit about polynomials. This guy, it's a cubic, right? If you think about the end behavior of a cubic, right? The cubics in general look like that most of the time, right? That's what a cubic looks like. Unless it has a negative out in front, in which case I just flip it upside down, right? Okay. So I'm willing to believe, and my evidence shows that at a -1 I have a maxima, and at 3 I have a minimum, right? But I'm bounding this thing on the left and on the right. So kind of made those little speed curves. Okay. So what I'm going to do is I'm going to say, all right, let's find out how high or low the function is at those endpoints. Okay. So all right. So what we have is we have 4 places that we have to carry out, 4 critical points. No. Okay, those are the 4 places that I have found that I need to care about. And it's a good idea to list them, because that's how you drop one. These were the bounds. How are those? And what we're not interested in derivatives anymore. We're interested in having the height of this function, because that's what we're looking for. We're looking for who is maxima, who is minima, what's going on with this graph. So all we're going to do is we're going to take these 4 values and we're going to plug them into the original function and see how tall the function is at those 4 spots. See what I mean? I know you're enjoying yourself, but at least you follow along. And then plugging it into the function. Gotcha. Good cover. All right. So go ahead and find f of -10, f of -1, f of 3, f of, and the original function. Yeah, it's based upon the amount of time it took me to complete service. It's kind of like between putting the pen up, taking the pen up. It's basically asking if you consider something continuous. So if the gap is less than a certain amount of time.
Okay. I have roll paper towels here.
That's right.
I had a student who's avoiding referral by cleaning all the stuff.
All right,
So what have we found? Some big numbers, right? Some of them are definitely large.
Yeah.
All right. So I'm going to go ahead and plug these guys in. So f of -10 is going to give me -1,000 plus 300 plus 900 plus 5, so 615. Negative 615.
Is it minus
So,
so negative on the square.
let's go through it. I got it.
That's negative.
Right. Yeah, I wasn't signed that. So negative 30, so 1, 2, 1, 1, 2, 5? Let's see. You lost the Now I'm going to plug in -1. Oh, you're doing the other side. So 11, 10. Oh, right, because I can't add. Yeah, that whole thing. It's like, yeah, calculus, no problem.
Yeah.
Adding,
That's what I feel like.
right. Wow. But, you know, the more you use, the less you use a calculator, the easier it is.
They've been around longer, but
700, 600, 10, 600. Alright, so, wow, there it is, in all of its gory detail. Wow, okay, now that we all come in, keep going. So, that's correct. Okay. So really what we have is something that looks roughly like, right? Actually, I should be probably a little more accurate. It's +5, so yeah, that's probably even a little bit more accurate. So at -10 and +10, we have these really, really, really negative and positive values. So they're both negative. So now we can say who is what kind of extreme. All right. This -10, this is the lowest possible point. So this is a global minimum. This fellow is high for his neighborhood, but he's not the highest in the neighborhood. No, neighborhood is actually a mathematical term. Oh, well, I mean, when you talk about the neighborhood of a point, it kind of gives you an idea about the curvature or what's going on in that area. Okay? Like, for example, the neighborhood of a cusp is very different than the neighborhood of this point right here.
Can you show us an example of the time that actually frequency of
Yes, I will. Next. No, it was my text. So relative next.
So I think it's not
We call it relative or local.
yeah.
Relative or local, yeah.
Let's be aggressive, sir.
But you define this. You define well.
Okay? So we can determine, first we find our points. Then we check the points for curvature. Then we check the extrema. The ends of my, the endpoints of my interval. And we find out who is relative and who is not. Okay? See this process? All right, let's write down the process in full-on words.
Oh, I have a question. What if one of the values that we get from doing this versus like the derivative is more than the
And that's fine. Like if you had an interval that looked like this. Okay. Well, that's fine. That's saying that this is not just a relative minimum, it's a global minimum. Because
but that's only within the bound.
within the bound, the function could go wow, weird on both ends. And go, you can have all sorts of weird endpoint behavior, right? Exactly.
I'm gonna look for that in the video.
Yeah.
That's great outside.
You are recording, right?
Take a picture outside.
There we go. The limit is x versus infinity. Alright.
How do you spell that?
W-A-A. Factorial. Alright. Alright, let's try a different example.
Do that on audio.
Wait, I thought we were gonna wait.
Oh, right, process. Okay.
Ooh, good one,
You're not
You were telling another time.
I'm gonna roll with it. I don't remember asking today. Ooh. And this step right here was one we didn't have to do in the last example, but we will have to do in the next example. So I'm going to write it in. Okay?
Okay.
Okay? That polynomial was defined along all real numbers. We didn't have a denominator equal to 0 or a negative square root somewhere or something like that. Okay, we didn't have to worry about that. But this time, in the next example, we will.
point rows of songs just to go really well. If they're not needed,
Yes.
that was the point.
Just George Benson and Monty.
It's like, I'm really cool. I'm sick. Yeah, oh, his brother.
Is he still Flash? Or you got big hair? It's small. I just saw Flash at college.
Hey guys, copy this.
Where does it?
Step seven.
What if this is at
No, no capital.
What I'm doing is at midnight.
That's still helpful. That's the fourth skill world.
That's a good one. Now you down, Ivy.
Absolutely. You're more than welcome to fall asleep in the middle of the IB exams. I can't guarantee what score you'll get, but you're more than welcome to do it.
She probably according to
She might visit you in your dreams.
All right.
I stretched last year.
Right. She would probably be there to wake you up. All right, no, that's important. Okay, so, all right, do we feel all right about this process? Do we know what we're doing at each step? It's a lot of algebra. But knowing what you're dealing with is important because sometimes you have a graph, sometimes you don't. You know, we will be doing, you will have your graphing calculator. Everyone has a graphing calculator on their own, right? I would imagine this is very hard. Well, I can. All right, let's try a different one. And the interval is -1. You can see all right, so this is your new thing to play with. Let's find and label all of the strings. You can hit 4, so you can do it on your paper. All right, so we made the substitution for the cube root, and now we took the first derivative. We're going to set that equal to 0, and we simplify. Good. All right. Now, let's go ahead and rearrange this guy for just a hot second. Shall we? All right, let's get a common denominator. So we have a couple of places that we're going to need to care about. Right? We're going to need to care about that denominator. So the denominator cannot equal 0. That is where my function is occupied. So
X equals 0 is definitely a critical point. Oh, not a critical point. It's a
point of investigation. That's where we need to care about. Points. So and 1. Those are two places we care.
We just got rid of the denominator.
No, I've got a common.
No. Have to get.
Oh, right. Because, yeah, if I multiply it on both sides, then now we're saying, well, I want to get rid of it by multiplying by 0. I'm sorry, by multiplying by both sides by the denominator. But remember, what we're saying here is division by 0 is no good. So these are places that matter to me. And we're also going to care about our endpoints. So it's undefined, it's critical points and its endpoints. So before we go anywhere, I want to check that critical value and find out its concavity. Okay. Because if you remember going back to that list I gave you in the previous slide, I believe it was step 4, said go back and plug in your values you got from step 2. Oh, yeah, sorry, was it step 5? Yeah, so we take the second derivative and we plug in it. So this is my first derivative. That's not my 2. Now remember, I could use, if I really wanted to, I could use this fellow, but then I'm using the quotient rule, which I really don't necessarily want to do. I'd much rather use this guy, which is just the product rule, right? You're going to give me the same thing anyway, so why not? That's a question for TOK. We don't do philosophy. We don't believe in philosophy. We don't believe in thinking. Gosh. I think this is. Right. So this is the derivative of 2 and 0. And I wind up with negative 2 times the negative 3/3 number. So x to the negative 4/3. Okay. I could, but all I really care about is plugging in 1 and seeing what the value of 1 is. So I'm not really, this is just kind of an intermediate step in the process of solving the problem. If I was looking for it to be my answer, then I would want it.
Are we just,
We're just plugging in 1.
oh, I thought this, oh, yeah. The derivatives are positive.
Right, and that's all I care about is concavity.
So if it's on any, so it's hard to report.
Yeah, and plugging in 1 at this point. Which is greater than 0. So is this guy caving? What does this guy look like at 1? It's a positive curve. It's concave up. We don't know if it's local or global. All I know is that it's a minimum. It could be the lowest point in the graph. It could be, just another point. Yeah.
It's okay if we use the term relative absolute.
As long, yeah, relative absolute versus global or local. It's the same kind of idea. Yeah.
Well, that's what we like. Yeah,
It's kind of counterintuitive. So let's check all of our points. We have -1, 0, 1, and 3. Plugging it into 3. Into that. So go ahead and find those 4 values. Yes, some of your answers might be goofy square roots. Right, cube roots.
Part of it is imaginary.
You won't get an imaginary because you're taking a picture. Sure, you can take the root.
Oh, yeah.
Yeah, you can't take an even root and get a real number. You can take a odd root and get a negative. With -1 to -1 to -1 to -1. -1 squared is -1. Was it? Oh, it's 2/3. I'm sorry.
Yes.
0. Thank you.
0.
0. It's 0. So go ahead and plug in those 4 values. What?
I thought there was only girls in the contract.
All right. It's weird. All right. So I plugged in the first 3, -1, 0, and 1, and I've gotten the following values. But I still have the last one, which is 3, and we're going to find out what's going on with that one. All right. So even without a calculator, we can estimate what's going on with this. We don't need a numeric value. Really what we need, because that's an exact value right there. I don't need a numerical rounded answer. But all we really need to know is it bigger than 0? Because if it's bigger than 0, if 6 minus 3 cube root of 9 is a positive number, then that means it's the highest point, right? Because right now I've got a -5, -1, a 0. All you guys are 0 or below. If f of 3 is positive, then it becomes my largest value, and that becomes my global maximum. So, in order for that guy to be positive, the cube root of 9 must be either bigger or smaller than 2, right? Because if it's equal, let's just say if it was equal to 2, then it would be 0, right? Well, what's the nearest cube?
8.
8 is the nearest cube. And since 9 is slightly bigger than 8, it's greater than 2. it's 2 point something something, right? So 2 point something something times 3 is 6 point something something. So therefore, 6 minus 6 point something something is negative point something something. Something something is the digit below 0. Right. It's this thing.
Something that's great.
So this is so this becomes my maxima. This is my low actually say that. It's global max. Global min. Local min. And now, since this guy is between 0 and 1, and negative 1, right? Is it a maxima, a minima, or what?
It's a global maximum.
What? Local.
It's between 0 and 1.
Yes.
Oh, relative maxima. And in fact, if you were to graph this, it would look like this.
Graph it.
Calculators, obviously.
Because we use a lot of This episode of the Rocco Show has been brought to you by Local and Global Maxima and Minima.